Hello, this is Andrew Mers, and I am presenting a case study in health, an application of deep learning to predict heart attack or myocardial infarction. A heart attack or myocardial infarction is when one of the heart's coronary arteries is blocked or has its flow dramatically reduced. Heart attacks frequently occur as part of heart disease, which causes the greatest number of deaths each year in the United States. Given the serious risk of death or serious heart damage from a myocardial infarction, predicting the incidence of such an event could be highly useful for purposes of prevention. For this project, a deep learning model was trained on data from the Health and Retirement Survey, or HRS, to predict the incidence of myocardial infarction over a 6-year period from 2010 to 2016. The Health and Retirement Survey was the data source for this study. This study is a longitudinal study of approximately 20,000 adults, mostly ages 50 plus in the United States. This survey seeks to understand changes in lifestyle, finances, employment, and health as Americans age. The first wave of this survey was in 1992. Respondents were re-interviewed every 2 years since. New respondents are periodically added to replenish losses and maintain the representative sample. Data from the 2010 core survey was used as the baseline for this project, and responses to follow-up surveys in 2012, 2014, and 2016 were used to determine whether a respondent suffered a heart attack within the 2010 to 2016 timeframe. A little bit of background on deep learning. Deep learning is a machine learning algorithm. It consists of an artificial neural network with one or more hidden layers. It is inspired and loosely based upon the functions of systems in the brain. It is made of connected layers of neurons with activation functions. Deep learning is commonly used for predicting an outcome based on input data, which could be structured data or unstructured data, such as image, sound, or text data. The goal of this project is to predict whether each survey respondent will have a heart attack within the 6-year time span of 2010 to 2016. For this problem, we will not be utilizing image or text data. We will be just relying on plain structured data from the surveys. Therefore, the type of neural network architecture used in this study will be a network with densely connected layers. Now for the process of reading the data and fitting the neural network model. We begin by downloading the data from the HRS website. The user must create an account and parsing this data. We downloaded the core surveys from 2016 or from 2006 to 2016 and the exit surveys from 2012 to 2016. Exit surveys were conducted when a respondent had passed away since the previous wave, where they attempted to follow up and ask any questions regarding the person's last years of life. The 2010 core survey was used as the baseline with a sample size of 22,000. Python code found in the Retrieve and Join Data Jupyter Notebook was used to parse the data from these files, join it together, and create the outcome measure of interest, which was whether a 2010 respondent had a heart attack between then and 2016. After creating this response variable, I determined that there were about 708 participants that had not been followed up in any of the waves since 2010. I decided to exclude these respondents because we didn't know whether they had a heart attack in the time frame or not. Next, the predictor variables for the model were selected. The predictor variables the variables used in the survey were defined in the HRS codebook. Please reference that to view what the variable names mean in the original raw data. So first, I looked at several different categories of predictors. First were heart attack risk factors, including age, tobacco use, high blood pressure, etc. The second category of predictors was demographic variables, such as gender, race, ethnicity. Lastly, I also looked at other health-related variables that weren't explicitly related to heart disease, but may have some correlation. These included height, weight, cancer, lung disease, arthritis, etc. I then performed an initial analysis on the data and noticed that about 950 participants were less than 50 years old. I decided to exclude these respondents from the analysis because they were a very small number relative to the whole sample size, and I wanted to focus on Americans ages 50 and plus for this predictive problem. Next, I performed exploratory data analysis. The goal of this analysis was to determine which predictors to use and how to code them. But before I did this, I split the data into a training and test set. I split it now because I didn't want the test set to influence how the model was constructed. I just wanted the test data to be used for testing the model on data I hadn't seen before. The training set was 16,000 respondents. The test set was 4,000. Henceforth, in the preceding analysis, only the training set was used. Next, using the training set, I determined the distribution of each of the predictors with respect to the outcome of interest, which was a heart attack within the 6-year window. Continuous or numeric variables were analyzed using overlapping normalized histograms. This allowed me to compare the distribution of the variable for the people that had a heart attack in the 6-year period and the people that did not. If there was a correlation in this variable with heart attack incidence, you would expect the distribution between those who didn't have a heart attack and those who did to be shifted. And you can see that this is the case in the graph in the bottom left corner. The older ages tended to have a higher incidence of heart attack than the people in the younger ages. For the categorical variables, I analyzed them using bar charts showing heart attack rates in each of the categories. For instance, in the bottom right-hand corner, you can see that those who never had lung disease had a significantly lower rate of heart attack than those who had an active lung disease, possibly due to the fact that lung disease correlates with tobacco use, and tobacco use is a heart attack risk factor. Next, the data was processed into a format that could be used to train a deep neural network. The first stage in this process was to recode the categorical variables. This was done by converting them into binary or dummy variables where 1 is true and 0 is false. For instance, in the high blood pressure variable, the value was 1 if the person had high blood pressure, and the value was 0 if they did not have high blood pressure. After recoding and selecting the final predictors, there were 39 total predictors, 5 of which were continuous and 34 which were binary. Next, I imputed the missing values. Values were missing in the survey due to non-response, as well as questions that were not asked to everyone. Variables with less than 10% of values missing were imputed using the mean for continuous variables, and the median for continuous variables, and the mean for categorical variables. Variables with greater than 10% of values missing, which were only categorical, were imputed using logistic regression. The logistic regression used all of the other predictors to predict the value for the missing values in those variables. Next, the data was rescaled. Neural networks work best when all the data is on the same scale. So I rescaled the predictor variables by subtracting the mean and dividing by the standard deviation. Next, before I explored different neural network model possibilities, I defined performance metrics by which to evaluate the performance of those models. The first metric was accuracy, which is the most intuitive measure. However, it could be misleading in cases where the outcome we're trying to predict has unequal proportions of the positive and negative class. Which is the case in our data set. Only about 5% of the respondents in the training set had a heart attack, whereas 95% did not. Therefore, we needed to look at other measures as well, because you could achieve a 95% accuracy by predicting they did not have a heart attack in any case. Some other measures we looked at then to help account for this were sensitivity, which is the proportion of the positive class, i.e. heart attack occurrence, that occurred that was correctly classified as a positive class. I also looked at specificity, which was the proportion of the negative class, not having a heart attack, that was correctly classified as the negative class. Additional measures looked at were the ROC curve and the area under the curve, or AUC. As a comparison, there is a comparison benchmark for the deep learning model. I first fit a logistic regression model using the 39 predictors. This logistic regression model attempted to predict the outcome. I used a classification threshold of 0.5 for this model. This model achieved a 95% accuracy with a sensitivity of 2% and specificity of 99%. This model predicted almost all the respondents would not have a heart attack, which wasn't very useful. However, we could improve the classification threshold. We could increase the sensitivity of this model by reducing the classification threshold. Next, I selected my deep learning model. I considered multiple deep learning model configurations and tested them using the Python Keras library. Each model was trained using an 80-20 training validation split. The randomly selected validation set was used to track the performance of the model in terms of accuracy, sensitivity, and specificity. For this model, I only used densely connected layers. I explored the following different variations of the following parameters: number of layers, neurons per layer, activation functions in each layer, the loss function, the optimization algorithm, regularization and dropout, which are means by which to reduce overfitting, weight initialization, training epochs, batch size, and learning rate, and class weights. So while testing different model configurations for the deep learning model, I ran into a couple of complications. Due to the highly unbalanced nature of the classes, the models had a tendency to ignore the positive heart attack class. To cause the model to pay more attention to the heart attack cases and thus increase sensitivity, a higher weight was assigned to these cases. After trying dozens of different model combinations, it became apparent that there was a significant trade-off between sensitivity and specificity, regardless of the model structure, possibly due to the limitations of the predictive power of the data. In order to increase sensitivity, usually the specificity would have to decrease. Therefore, I decided to define a satisfactory model as one that identified a majority of the heart attack cases, that is, had a sensitivity greater than 50%, while at the same time minimizing false positives, having a specificity greater than 75%. After choosing my optimal model, neural network model configuration, I needed to determine how many epochs it should be trained for. I did this by fitting 10 models of the same structure, training each of them for 50 epochs, and then plotting the sensitivity, specificity, and accuracy of all 10 of these models averaged with respect to epoch. The optimal number of epochs was selected as the point where sensitivity was at least 50%, specificity was at least 75%, and the accuracy was maximized. I ended up choosing 5 epochs as the optimal number to train the model using this methodology. The final model, after a lengthy search, was chosen as the following. It had 3 layers. The first layer was 100 neurons with a ReLU activation. The second layer was 10 neurons with a ReLU activation. And the third layer, which was the output layer, had 1 neuron with a sigmoid activation. The loss function was binary cross-entropy. The optimization algorithm was atom. There was no regularization or dropout. Weighted initialization was normal distribution. 5 training epochs were used. The batch size was 100. The learning rate was 0.001. And the class weights were such that a non-heart attack or a heart attack case had 15 times the weight of a non-heart attack case. I then tested the model on the test set, which had a sample size of 4,000. I found that the model had about 78% accuracy, a sensitivity of 56%, a specificity of 79%, and an AUC of 0.75. And as you can see in the ROC curve down here in this figure, the ROC was pretty similar between the logistic regression model and this deep learning model, indicating that overall these models had similar performance. In conclusion, the deep learning model was able to identify the majority of heart attack victims, although it still missed a significant number, 44%. Conversely, it had a false positive rate of about 21%. The much simpler logistic regression model achieved practically the same performance, demonstrating that a more sophisticated model does not always perform better. To improve the performance of the deep learning model, several options could be considered in the future. Implement an exhaustive grid search to explore a larger portion of the parameter space and have a higher likelihood of selecting the optimal hyperparameters for the model. K-fold cross-validation to get better performance estimates on using the validation set. Explore the data set further to identify additional predictor variables, and refine the logistic regression models used for imputation so that the imputed values are more accurate. Overall, I'm pleased with the results of this analysis, but more work remains to be done in order to improve the quality of the deep learning model. Thank you very much.